Welcome to using substitution to evaluate trig integrals. So recall, we know that the integral of cosine of x dx is just sine of x plus c. And the integral of sine of x dx is negative cosine of x plus c. But we have not yet seen the other four trig integrals. It turns out that we can evaluate the remaining integrals or remaining trig integrals using substitution. So for our first example, let's go ahead and use substitution to evaluate the integral of tangent of x dx. So just a quick reminder here, recall that tangent of x is the same thing as sine of x divided by cosine of x. So we can rewrite our integral using this format. So the integral of tangent of x dx is the same thing as taking the integral of sine of x over cosine of x dx. Now we do have a little composition going on in that sine of x over cosine of x. So we have a composition. We have an outside function of 1 over x. We have an inside function of cosine x, and that sine of x in the numerator happens to be precisely related to the derivative of our inside function cosine of x. So let's go ahead and set cosine of x to be our u. So we'll set u equal to cosine of x. Then we have that du is a negative sine of x times dx. Again, when it comes to trig functions and integration and differentiation, watch very carefully which one we're doing for the cosines and sines to make sure your positives and negatives come out correctly. So if we differentiate cosine, we get negative sine. This means that sine of x dx is equal to a negative du. So we have our integral of tangent of x dx is equivalent to the integral of 1 over cosine x times sine of x dx. That can be written as the integral of 1 over u times a negative du. I'm going to give myself a little bit more room here. This becomes the integral or negative, the integral of 1 over u du. That, of course, is a known integral. So we get negative times the natural log of the absolute value of u plus c. At this point, we can go ahead and plug in. We had that u was equal to cosine of x. And so we have that the integral of tangent of x dx is equal to negative natural log of the absolute value of cosine of x plus c. Or if you like, you could rewrite this as positive natural log of absolute value of 1 over cosine, which is and then plus c. And of course, that is the same as the natural log of the absolute value of secant of x plus c. So these are all equivalent forms for the integral of tangent of x dx. Next up, let's go ahead and use substitution to evaluate the integral of secant of x dx. So secant of x is just 1 over cosine, but that does not lend itself directly to u substitution. So we are going to force a very odd u substitution. So we will force a substitution by multiplying by a version of 1. And that version of 1 that we are going to use is 1 is equal to secant of x plus tangent of x, whole thing divided by secant of x plus tangent of x. So it seems slightly odd, but you will see why we did this in just a moment. The integral of secant of x dx therefore becomes the integral of secant of x times secant of x plus tangent of x over secant of x plus tangent of x dx. This can, of course, be rewritten as the integral of, in our numerator, we'll have secant squared of x plus secant x tan x. And in the denominator, we will have secant of x plus tangent of x. Then that whole thing has been multiplied by dx. Now note, secant squared x is precisely the derivative of that first term, secant x, in our denominator. Secant x tan x is precisely the derivative of tangent x. So note, secant squared of x is the derivative of secant of x. Sorry, is the derivative of tangent of x. Sorry about that. I had my terms in reverse. So secant squared x is the derivative of tangent of x. Secant x tan x is the derivative of secant of x. And so what this means is that numerator is simply the derivative of the denominator. And so it makes sense then to go ahead and name that denominator as our u, and the du just falls directly out in the numerator. So let's go ahead and set the denominator as our u. So in other words, u is secant of x plus tangent of x. Then our du is secant x tan x plus secant squared x whole thing times dx. What we get then is that integral of secant of x dx is simply equal to the integral of 1 over u times du. Therefore, we get the natural log of the absolute value of u plus c. Then if we plug in u equals secant x plus tan x, we wind up getting our formula of the integral of the secant of x dx is equal to natural log of the absolute value of secant of x plus tangent of x and the absolute value, and then plus c. So there's our formula for the integral of secant of x. Now, the only two trig integrals remaining use a very similar process to solve as the ones we just did. So I'm just going to directly give you those formulas. So our two remaining trig integrals, we have the integral of cotangent of x dx. Recall the integral of tangent was negative natural log absolute value of cosine x plus c. Turns out the integral of cotangent is a positive natural log of absolute value of sine of x plus c. This one can be found by performing a similar process as was used for integral of tangent. So this can be found similarly to the integral of tangent of x dx. Then the integral of cosecant x dx. Integral of secant was a positive natural log of secant x plus tan x plus c. Integral of cosecant is negative natural log of the absolute value of cosecant of x plus cotangent of x and absolute value plus c. And again, this one can be found similarly to integral of secant x dx. So as you saw with secant, u substitution is not always obvious. Sometimes it requires some weird manipulations to make it appear. But u substitution is a very useful trick for finding a variety of integrals.